Hi guys. I've come up with an alternative for Project 7 that doesn't involve PID loops and feedback because we don't have the PSOCs. We're not in the laboratory actually. We're doing everything virtually. So as an alternative, I am going to have you guys investigate just building circuits with motors. That was part of the original Project 7, an important part of it. So we'll get a lot of the benefit of that. It just won't be quite the same as being in the actual lab. Um, so here's the thing I want to emphasize is that the project goal, here let's emphasize this here. You're going to build a circuit that's going to use some sensor. You can use any sensor you like that's available to you in TinkerCAD, and use that sensor to control a motor. So it either needs to, depending on the type of motor you have, it either is going to control the speed of the motor or it's going to control the angle of the motor. So and I'll show you some examples here of how that might work, what that might look like. You can also use either direct control, just by controlling the pins on the microcontroller. If you're using, well, you'll be definitely using a microcontroller. Well, if you have any sense, you'll be using a microcontroller. There are multiple ways of controlling motors with microcontrollers. There are some built-in libraries you can use. There are also motor controller circuits you can use, and I'll introduce you to all of that here in just a minute. But the idea, basically, just to reiterate, is you pick some sensor that you think looks interesting in the library, in the available sensors on TinkerCAD, and you need to control a motor, either a servo motor or a DC motor, using the input from that sensor. Does that make sense? There's a bunch of different sensors you can use. I'm not going to get into that. You guys know about sensors. The two types of motors we're going to be using are either simple DC motors or servo motors, and I'm going to describe those in a moment. But basically, a DC motor you control by either adjusting the voltage that's used to power the motor, which is not that easy with a microcontroller, or you adjust the duty cycle of the power, which is relatively simple to do with a microcontroller. So that's the approach we'll probably take. That's the approach I suggest you take in this project. So, okay, let's go look at a couple of examples. I'm going to start with this one. So this example is public. I'll share a link to this guy in the GitHub repository once this document is ready. I'll be posting this shortly. So this is a simple circuit. It's got power. It's got a voltmeter here that's measuring the voltage at the wiper of this potentiometer. A potentiometer is just a resistance. There's a resistor from power to ground, and then there's a wiper. Let's see. You know, I always think of this after I get started here. Let me just pop in here and Google potentiometer. I think we might have used one of these before. This is the schematic symbol for a potentiometer. It's just a resistor with a wiper. And if the wiper is at this end, if the wiper, so if the wiper is at this end of the potentiometer, it has whatever voltage is at this end, and if you move the wiper down to this end, it has what voltage is at that end. So basically you tie one end to 5 volts and one end to ground, and then you run the wiper back and forth to get a voltage between 5 volts and ground. That's the idea. So let's see, what am I doing here? Oh yeah. I should show you this. This is the section in the textbook that you guys use for Physics 163 that talks about motors. So you can remind yourself of that if you still have your textbook. But let's go back to the circuit. If I run the circuit, you can see that if I run the potentiometer to one end, I get 5 volts out. If I run it around to the other end, I get 0 volts out. So the potentiometer just adjusts the voltage coming to pin, whatever this, PB3 of this microcontroller. This is a microcontroller called an AT-Tiny. You're welcome to use this one if you wish to. They're really nice because they're extremely small. You just supply, they're little 8-pin packages, so you can supply power and ground, and then you've got a microcontroller. You don't need a full-blown Arduino necessarily. You do have to program them separately. Whoopsie. You have to program them and then outside of the breadboard, and then plug them into the breadboard to actually use them. So they're not quite as convenient as an Arduino in many ways, but they're on TinkerCAD they're quite easy. You can simply pop open the code. It looks a lot like an Arduino program. Let's actually look at what this code is doing. So we've got a variable called analog data. Analog data is just whatever it's reading from this pin, which is just coming from the potentiometer. So I'm just reading in a number between 0 and 1023. It's a 10-bit analog to digital converter. And I'm converting that to a delay in microseconds. I'm using the map function, which simply does a linear map between, it has an input value, and then it has a low and high for the input, and then it has a low and high for the output. And it simply performs a linear map between the input range and the output range. In this case, it's taking a number from 0 to 1023, and it's producing a number from 1000 to 2000. So if you put in a 0, you get 1000. If you put in 1023, you get 2000. And if you put in anything in between, you get something in between. But notice what it's doing here. It's bringing PB1 high. It's delaying for a number of microseconds between 1000 microseconds and 2000 microseconds. So 1000 microseconds, of course, is a millisecond. 2000 microseconds is 2 milliseconds. So it's delaying, it's keeping the pin PB1 high for a period of time somewhere between 1 millisecond and 2 milliseconds, depending on the value of the voltage that it reads from the potentiometer. And then it brings PB1 low as soon as that delay is over. Now this math down here is simply to calculate how much time is left to try to produce an output waveform with a period of 20,000 microseconds. And 20,000 microseconds is approximately 20 milliseconds, right? So it's going to put out a pulse every 20 milliseconds. The pulse is going to have a duration of between 1 and 2 milliseconds. And so that's it. That's the idea. That is, in fact, how you control a servo motor. A servo motor, let's go ahead. You can see here right now, if I dial this thing, let's go ahead and bring it down to 0. And you can see that at 0 volts on the potentiometer, we're getting an output pulse of about 1 millisecond on the on this line, this PB1 line. And that 1 millisecond pulse is getting sent over to the control pin or the signal pin of the servo motor. The servo motor has power, it has ground, and it's got this control pin. The control pin is controlling the angle of the servo motor. And we're sending out pulses of 1 millisecond, so the angle is all the way to the left. If I dial this thing around, the angle goes all the way to the right. Now we've got a pulse of about 2 milliseconds, and that's basically the way it works. So a servo motor simply uses the pulse width of the PWM waveform to determine the angle that the servo sits at. So that's the whole idea. I'll stop this one. Okay, so let's go back. I want to go here. So that's how you control a servo motor manually with PWM. Let's look at the servo library. Let's see if I go back here, pop back to my circuits. Here's another way to control a motor. Let's go ahead and look at this one. Now, this is using a motor controller that it takes, let me go ahead, oh yeah, okay. It takes power and ground. The power and ground on this side is high current power and ground. In this case, it's a 9-volt battery, and that's used to to deliver power to the motor, but notice we don't connect directly to the motor. The motor is connected to output A and output B, which are connected to power based on this motor controller. The motor controller it has a number of ways that it can potentially work, but the way I'm using it is through the remote control interface, the RC interface. I'm using RC pin 1, and I'm connecting that to pin 3 of the Arduino. Notice that the ground is connected, the ground of the Arduino is connected to the same line as the ground of the motor, which is connected to the ground of this 9-volt battery. So these guys are all connected together. I'm also supplying power here, but I'm not actually doing anything with the power. So the breadboard here is not doing very much. It's just there to share a ground. I probably could have skipped it. But let's look at the code in the Arduino. So I'm including the servo.h, and I'm using the servo library this time. So instead of manually controlling the PWM signal, I'm just using the servo library, and then I'm using the motor right command to set an angle. The angle is between 0 and 180. That's because this is often used to control servo motors, which have a fixed angle between 0 and 180. 90 is considered neutral, 0 is all the way to the left, and 180 is all the way to the right, which is kind of how they work. But the way this motor controller works, it views 90 as 0 speed. 0 is full speed to the left, and 180 is full speed to the right. So it's just a different interpretation of angle in this case. So let's go ahead and run this thing, and you can see how it works. What's happening is, let's look at the code. What the code is doing is it starts the angle out at 0. Every time it goes through the loop, it increments the angle by 1. If it ever exceeds 180, it sets it back to 0. And so it's just iterating, adjusting the angle from 0 to 180 and then back to 0 again. So you can see what happens is when it starts out, the RPM is negative, but it's less and less negative. It eventually slows down. Let's zoom in here. It slows down to 0, and then it starts getting positive. It'll grow more and more positive with time because we keep increasing that signal, and then it flips back to negative again because it got back to 0. So basically what happened, the way this thing works is this motor controller allows you to pretend that your DC motor is a servo motor. It does the control and determines the speed, but it does it with the Arduino can treat it like a servo motor, but actually it's a DC motor that's just using the servo convention of 1 millisecond to 2 millisecond pulses in order to control the speed of the motor. So this is probably the easiest way to attack this project. So finally, let's go to the last option, which is, let's see, here we go. This one. This is an Hbridge circuit. So let me pop back to the handout. So the other way to control a DC motor is with an Hbridge chip. So that's this guy. This particular one is the L293D. The D means that it's got diodes that protect the chip and protect the electronics from inductive kicks from the motor. So those are all baked into the chip itself. Let's see if I can find a data sheet for this guy. I think I've got one here somewhere. Here we go. So this is the Hbridge chip. Let's just pull up a pinout. It's got an enable pin for sections 1 and 2, and then it's got a separate enable pin for sections 3 and 4. For a single DC motor, you only really need one section. You can use 1 and 2, or you can use 3 and 4. Internally, let's see if we can find an internal picture here that shows you what's going on. Here we go. So the way it works is you can either run the motor forwards by setting this pin high and this pin low, or you can run the motor in reverse by setting this pin low and this pin high. It basically routes power to the motor in one direction or the other direction, depending on the relative polarity of these two pins. So pin 2 and 7 are control pins. Pins 3 and 6 are the power pins for the motor. 4 and 5 are ground. 1 and 1 is the enable that enables this whole side of the Hbridge. And then pin 8 is motor power. Notice there's two powers here. There's motor power, and then up here there's power for the I don't know if you can see my mouse or not. There's logic power, that'd be 5 volts, and then down here this is the guy that's for motor power. So this will be our high power. So we'll see how that works here in the TinkerCAD. So notice I've got a 9-volt power supply, and I've also got an Arduino. I'm separating, there's two power lines. There's 5 volts, which I'm using this upper power line, and then this lower power rail, I'm powering with the 9-volt battery. And they're not connected. Notice there's no connection between the plus power on this rail and the power on this rail. And that's deliberate. We don't want to connect 5 volts to 9 volts. That's not going to end well. The ground here I connect to, the 5 volts I'm connecting directly to the power 1, which is the logic power, and I'm routing that around to the enable pin for this side of the Hbridge. I'm not using this side of the Hbridge at all. We're just leaving that disconnected today. The control pins, control 1 and control 2, are being controlled on the Arduino by pins 3 and 5 here, which are both PWM outputs, which is important because I'm going to be using the analog write PWM control to control the duty cycle of the control pins on the Hbridge, and that'll control the speed of the motor. And then finally the actual output here, and output 1 and output 2 are for power to the motor itself. So let's go ahead and look at the code. It's quite simple. Let's actually change this to pin 3. I'm going to and let's set this to 127. So we'll run that about a half duty cycle, 50% duty cycle, and we're getting an RPM of negative 8,000 or so. Okay, I'll stop that. Then let's change the duty cycle to 255. That means it's on all the time. It's going to run flat out as fast as it could, about double that, negative 16,000. So that gives you an idea. If I dial this thing down to, 50? That'll be 20% power. And we'll see what we're getting. It's about negative 3,000. Okay? So that kind of makes sense. What if we want it to run the other direction? Well, then I have to make pin 3 low and make pin 5. We'll make pin 5 high. And that should run the other input, and notice now we've got plus 3,000 RPM. So depending on which of the two inputs I drive, I'll either get the motor going one direction or the other, and then depending on the duty cycle of that drive, it'll have a different speed. So you can adjust the speed and the direction using this single Hbridge chip. Okay, I think I've covered it all. Let's go back and double check. Where was it? I was sorry. I need to go here. Okay. Yikes. Okay. So we talked about the Hbridge chip. We talked about direct manual control of PWM. We talked about using the Servo library. Those are the three options for a regular DC motor. For a servo motor, you can simply directly manually control the PWM, or you can use the Servo library. You don't need a motor controller because the servo motor has that sort of baked in. So I think that's it. All right. Please ask if you have questions. I'm also going to post a separate video about the statistics exercise for this week, which will be the same as it is the original statistics exercise for Project 7. So we should be good there.